Math and programming, they belong. When you're good at both, you have the power of the world at your fingertips. You start looking and performing wizard-like actions. But you're not so good at math.
You shall not pass!
People are going to start asking you to do math to solve who asked.
Now, if the person who asked is imaginary, and the square root of -1...
Well, you're in some luck, because the math I'm going to show you today is simple, and it doesn't involve crazy things like derivatives. But I'm going to teach you how to take your simple programming and make it look impressive with some simple math. This is actual footage of a baby that was really impressed by my programming.
Join us now and share the software. You'll be free, hackers. You'll be free.
All right. First things first. Bouncy balls. Easy peasy, lemon squeezy. First, let me explain velocity. Velocity, speed, pretty similar. The only difference, velocity determines the direction of speed. Now, if you want to know how fast you're going downwards, you can use this formula. So V is velocity, G is gravity, and T is time. Now, I know some of us are planning on living in Mars, so maybe this might not be that applicable to you. Gravity is usually measured in meters per second, and T is usually measured in seconds. So you can change the units around with this, but that's typically what I see being used. And gravity is normally about 9.8 meters per second, but it can depend on your different variables like how high you are. This is the velocity for determining your upward motion. So after the ball hits the ground and you come back up, this is the formula for the rising of the ball. V is velocity, E is restitution, B is also velocity, and G is gravity, T is time. So just to be clear here, you're changing the velocity every time the ball hits the ground and starts going back upwards. This formula is going to be performed every time the ball hits the ground, and it's going to keep diminishing the velocity. Restitution is always a fraction. If it wasn't, it'd be increasing velocity each time. These are typical values for different types of objects. And this is just, displaying a bouncy ball. This is the ball. This is where the center of the ball is. At this position, this is the radius. This is saying whether or not it's going down or up. True if it's going down, false if it's going up. This is my restitution value. I set some initial values. You see that this is static, so it only gets initialized once. Anything in these static variables are initialized once. You got an initial Y position, so that's the starting, position where you dropped it at. That's how high you dropped it from. Y is the Y value, and it'll keep changing over time. This is what I named this restitution, but yeah, this is what is the increment, how restitution is gonna start at 1, and then it's gonna keep multiplying e to it, so keep slowing down the ball. F is actually time, and this is acceleration. So if the ball is going down, this is what the formula we showed before. Gravity times time, and that'll equal our velocity, or I'm calling this, in this case, this is acceleration because it keeps incrementing it every tick, so I'm calling it acceleration here. And then if we're going upwards, we're doing restitution minus gravity times time, like I showed before, somewhat. And it might look a little bit different here because I changed it a little bit. So then we have the center of the ball, right? I'm adding acceleration to the y value, so it's going to keep getting faster and faster as it goes down. And these are values that I'm not even using, but I'm calculating anyways. And then we're going to determine if the ball, which is the center position of the ball plus the radius. So if you got the center of the ball and then you add the radius, that's going to tell you the distance from the center, which is going to tell you that, it's going to give you the bottom part of the ball. And if that bottom part of the ball is greater than equal than the screen rect and restitution is greater than 0, we kind of want to clamp restitution. I probably could have done a better, I need to clamp the velocity. I could have done a better job at that. Then we set the time back to 0. Now the ball is going up, and then we multiply our E value to the restitution. So it's gonna, as it goes up, it's gonna keep going, up, but not as high and slower. And it's gonna keep going up, not as high and slower. And then we're gonna draw, and this is just checking to see if the ball goes out of bounds, and this is just gonna draw the circle or the ball, whatever. Yeah, and you can see how this works, and then it's gonna go through it again. And then it's going to call update main again. That's what this does. And it's going to keep looping through this until the ball stops. So this is just an example of what it looks like. Boom, 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 boom. And then it's going to stop. The reason why we clamp the velocity of the ball going upwards, because if we didn't, what would happen is that the restitution value that, keeps making velocity smaller and smaller would just keep getting so small, and the ball would keep bouncing almost infinitely. So what we need to do, and what people normally do, is that when the velocity gets really close to 0, or in this case I'm calling it restitution, it's the same thing in this case, just stop. Don't do anything anymore. Hang on. I think I'm getting a call from someone. Hello?
Hey, Austin, if you don't create more lines of code, you're going to be fired.
All right. So Elon Musk said it himself. We got to do something more. Something different. Something better. How about Angry Birds physics, 2D projectile motion? So for this, we're going to have to know what the velocity of y is going to be. And that's this equation here, where delta y is the change of the y value. This, you might have remembered this. So if you have the final position minus the initial position, that'll get you delta y. And then we have the initial velocity, which is v0, and that times time, plus 1/2 times acceleration. Remember, we learned what that was before, times time squared. So this is the formula for our x velocity, which is the change in the x, or delta x, which is, the final position minus the initial position, which equals the initial velocity times time. Then we're going to need to figure out the angle of our trajectory. So that's, the angle we're going to launch the ball at. We have to think back to trigonometry. Remember SOHCAHTOA? Well, we're going to need opposite divided by adjacent, which was what? TOA? T-O-A. But the problem is, if we do that, we're not going to get the angle. So we need not tan, but inverse of tan to get the angle, which is arctan. And this is how we're going to find the initial y velocity. So y0, or y, the initial value for y, is going to be equal to negative L initial times sine, and then the angle that we got earlier, the angle of the trajectory. So L0 is, if I have to explain this, it's an initial value that's gonna be multiplied to make the velocity higher or lower. And we also have to keep in mind that for the when you're drawing to a screen, 0 is at the top, and then it goes from 0 to the height of the screen. So it draws downwards. So the highest value is at the bottom and not the top. Then we're going to need to get the initial x value. This is a pretty similar, except we're gonna do so the initial x value x0 is equal to the initial L value L0 times cosine times the angle of trajectory that we got earlier. And understand why we're multiplying by sine for y and by cosine for x. It's you kind of have to understand the unit circle. The measurement we're getting, the angle of trajectory, is in radians. And I'm going to explain this simply. This is the unit circle. You don't have to really understand what this is, but these are the values, these pi values that you see around here. Pi divided by 3, pi divided by 4. That's that's the radian value for each degree around the circle. You don't have to completely understand that. Just know that usually sine of the radians, just sine is used for y, and cosine is used for x. And when you put those values together and they have the same exact angle and you keep increasing the radians, you're going to make a circle. This guy does a pretty good representation of what that looks like. So if you're curious on how that works, just look at this video for a second and it might make more sense to you. We're also going to have to remember the Pythagorean theorem, which just states that a squared plus b squared equals c squared. This works with right triangles, and c squared is the hypotenuse. A squared and b squared are any other side of the triangle that's not the hypotenuse. All right, so here's the code right here. We have draw path and update. Update just happens, as the game progresses, or as the program progresses. So draw path is getting that initial velocity that we've seen before, right here, if we remember that formula, and it's getting the initial x velocity that we've seen before. And then we're going to use our formula for delta x right here. Then we're going to use our formula for delta y. And then what we're going to do is take that delta x and delta y, and we're going to keep incrementing that circle, the center point of the circle. We're going to keep adding delta x and delta y to the center point to change the position of the circle. And then this is just displaying information to the screen, this printf. And then we're going to draw the ball with, this is the x and y position, and this is the radius, and this is the color for the ball. And I put delta y is less than or equal to, if it's less than or equal to -1, I actually don't know why I did that, but I did it. I'd have to relook at the code to remember why I did that. I think it's only going to hit, it's only going to happen at certain points, but I don't think I needed to do that. So then on the update, so we got that this is the draw path. This is just going to draw the circle and then draw where it's moving to. Then we have the update, which has a little bit more to it. So first we're going to need our static variables: launch start, launch angle, and launch initial, which is that L value that I showed you in those formulas. We have a point, And this point is the starting point for the ball, where it's going to start before it gets launched. And then we're going to, set a color for SDL to draw. Then we're going to draw a line from our mouse value. And this is going to happen, when the mouse is clicked. We're going to draw a line from that point, this point, to wherever our mouse is at. And that's going to determine our L value, or our initial launch initial. Our launch initial, which is going to determine how much velocity we're going to have, initial velocity we're going to have when we launch it. And we're also going to need the angle. So to figure out the angle, and remember the formula we used before, right? So we're getting the opposite and the adjacent by, taking, when our mouse is, out at a specific spot, we're going to get the opposite by doing, mouse Y minus point Y, and then the adjacent by getting mouse X minus point X. And then the formula I showed before for finding the angle and radians. Then we're going to set the color to red. We're going to draw the line. And no, this line is, what line is this? Ground height. Oh, this is just drawing the ground. That's what this is. And it's just going to draw the ground red. And then when our mouse, I think it's 1 is when it's clicked. Then we're going to get the start time for the launch. And then we're going to get the angle. And then, this is the formula we showed before. So this is drawing the line for the initial launch right here. This is actually getting the length of that line. And, that's just, a squared plus b squared equals c squared. And then if we want to find c squared, which is the hypotenuse, you're going to have to do a squared, which is opposite. Then adjacent is b squared. And then we're going to have to square root that. That'll give us c squared, and then we'll have to square root that to get the initial launch. And then we're going to see if launch start is greater than 0, and that's the time that it started, then we're going to start drawing our circle. And that's pretty much it. This is kind of what the program looks like. Let me make it and run it. So we got a ball going through the air, and then we can see that how it's slowly going up and then slowly going down. It's making I forgot the name of that curve. There's a special name for it. I don't specifically remember, but yeah, there you go. Now, I don't know about you, but that seemed a little too simple. Let's do something a little bit more in depth. Let's move on to elastic collisions. And in order to do this, we're going to have to understand a little bit more about linear algebra. We're going to need to understand what a vector is. And a vector can be either a 1 by n vector or m by 1. Basically, all that means is it can be represented horizontally or in a row or vertically in a column. Just think of it as a list. A list of numbers, and you can represent magnitude and direction. Magnitude being the size or length or whatever of something. We're going to have to also understand how to get the magnitude of a vector. So whenever you see a vector, it's usually a letter with a line over it, or an arrow over it, like that. And then the magnitude would be the two vertical bars to the left and the right in that image you see there. So that would be for finding the magnitude of vector A. And then to do that, you take all the elements in the vector, you square each element, add them all up, and then take the square root, and that's your result. You'll notice here that this is basically pretty much just the Pythagorean theorem. What's also really useful to know is how to normalize a vector. The U with the little hat over it means a normalized vector. So to normalize a vector, you just divide the vector by the magnitude of the vector. This is useful because you can get a direction with also having a magnitude of 1. And that can be helpful for all kinds of reasons. Then there's dot products. So whenever you see one vector, a dot, and another vector, like you see with A and B above here, that means find the dot product of those two vectors. And you can find a dot product by taking the first element of both vectors, multiplying them together, then adding it to the next multiplication of the next elements in both vectors, and then you keep doing that and you get your dot product. Sometimes when using a Cartesian plane, x and y graphs, same thing, you want to find magnitude and direction. And if you just use the formula to find the magnitude of a vector or the Pythagorean theorem, you're not going to get the direction component. So what's helpful to do is get a normal vector that's pointing in the direction you want to find a magnitude for, then multiply it by the vector you want to find a direction in and magnitude, and that'll give you your answer for x and y, and we do this for x and y. To find if two circles are overlapping, we just use the Pythagorean theorem. We take a squared plus b squared, take the square root of that, absolute value of that, see if it's less than or equal to the sum of both the radiuses. A and b are derived from the center points of both circles. Finally, we have to look at elastic collisions. In a nutshell, what elastic collisions is what happens when two objects collide. In this case, we want to get the velocity of object 1 and object 2 when they collide and know what the new velocity is. And that's the formula for that. V1 is the first object, V2 is the velocity of the second object, M1 is the mass of the first object, M2 is the mass of the second object. This only applies when a front-on collision happens, and this is the velocity in the opposite direction. This doesn't account for the sliding collision. The sliding collision, there is going to be no elastic collision happening. So the code I'm about to show you, a lot of it was taken from this guy, and he did a video on circles. The video is called Programming Balls, number 1, Circle versus Circle Collisions, C++. I took a lot of that out, and instead of I didn't use C++, and I didn't use his little rendering engine he has. I just used C, and I used SDL for rendering images and whatnot instead. And I changed little parts of the code around, and I'll mention that when I go through the code. All right, so let's look at the code. We have a function for getting the hypotenuse. A squared plus b squared, the square root of a squared plus b squared gets us our hypotenuse. Then we have ball collide. And you'll notice this is the circle collision or circle overlapping formula I showed before. You'll notice it's a little different than the formula we've seen, and we took out, or in the code I examined, he took out square root because it took up too much processing power. If we didn't take out square root, it would look more like this. or it would look like this, not more like. But the problem with this is what I already said, is it takes up too much processing power. And then I'd find the absolute value of this, or fabs. I don't know why it's fabs and not abs, F, but yeah, that's what the formula we've seen. But instead of him doing that, he just multiplied the sum of the radiuses to get rid of the square root. It's computation. Then finding if the points are in the ball is pretty similar calculation. The only difference is we only have one radius, so we don't need to multiply a second radius. Our draw circle formula, which I've went over before, just using cosine and sine to draw a circle to the screen. And then draw a ball is using the standard circle formula, which draws in a filled circle. Or, yeah, filled circled ball, whatever. And then we can look at the main game logic. So elapsed time is how much time has passed by inside of the function for what I need to compute. And then selected is the selected ball. -1 meaning no ball selected. I'm going to fix that. This is an array of balls colliding. This is how many balls are colliding and the count to be used with that array. And this part is right here is handling some of the mouse clicking. So what happens is when I move my mouse around, and if the mouse cursor is inside the ball and I left click, while left click is held down, the ball is selected. While that ball is selected, I can move it around. If the ball is also selected and I right click, the ball will not be able to be moved around, but will still be selected. And I also have the new ability of being able to drag in any direction. And that, by me dragging, it'll make a line from the center of the ball to my mouse pointer. That distance from the center of the ball to my mouse pointer would determine the velocity the ball will be launched in. The ball will be launched in the opposite direction that vector is pointing in. And let's get to this first loop that's looping through all of the balls that are on the screen. And we're going to loop through all the balls, get the ball, and then this is going to add drag, which is a negative acceleration, and we're going to times this value to it, which is just a fraction, so that it'll keep decreasing and decreasing. So we're going to take our velocity, and we're taking this acceleration, which is just the drag, and multiplying it by time. And this drag is just going to make this value is just going to keep getting smaller and smaller. Then we're going to get our velocity for the balls, and this will be our positive acceleration for X and Y. And after that, so we just went through this. Now we're going to do the clamping velocity like I talked about before. So the ball is going to keep moving and moving and moving and moving, and it's going to keep slowing down, but we want to stop it when the velocity gets really close to 0. So we're going to use our handy dandy dot product to determine what the velocity is in whatever direction it's traveling in. Take the absolute value of that and determine if it's really close to 0. If it's less than a value really close to 0. And if it is, just set velocity to 0. Stop the ball from moving. No moving for the ball anymore. I clear the screen, set it to black. And then this next loop is just rendering the balls, drawing them to the screen. I'm going to draw a ball that's filled, which is what draw a ball does. If it's selected, if it's not selected, I'm just going to draw a circle, and that's a ball that's not filled in. Then we're going to go through 2 loops. So when I looked at his code, he did j equals 0 here, and then he did a thing like, this isn't exactly what he did because he was writing it in C++. Syntax, the way he was doing things was different. I go with the never nesting approach, and I try not to nest things if I don't need to. But anyways, so the reason why I don't do this, this is just so that I and j aren't the same values. You're not comparing the same exact ball. The problem with this is you still are going to compare the same exact ball when you loop through things like this. What might be better to do is what I did, like this. And that way, you won't compare the same 2 balls more than once. So if the balls are colliding, ball 1 and ball 2, then we add it to the ball colliding array. And this is just, us adding it to the array. And then we're going to get the distance between the 2 balls using the Pythagorean theorem. And then we're going to get the overlap between the 2 balls. And how we're getting the overlap is we're taking overlap is we find the distance is we have the 2 distance between those 2 centers. This is the distance between the center of the ball. I'm sorry. We have the distance between the center of both balls. And if we subtract both of those radiuses, if they're perfectly touching, that would be 0. But if there's a negative value after subtracting the distance from both the radiuses, then there's overlap. So that's, that would say that there's overlap. And we know that there's overlap because the ball colliding thing already tells us that. So this should be a negative value. But there could be a case where they're perfectly touching. So to handle that, if the distance is equal to 0, just skip the rest of the logic because we don't want to divide by 0 error. And then this should look familiar to you because we have, we're getting the normal vector. Or the unit vector. I think it's also called the unit vector. So we're taking the distance for x, or I'm sorry, the vector for x. This is the x vector, and then we're dividing it by distance. And what do we get? The normal vector, which is a direction, right? So we got the direction for x, the direction for y, for ball 1 and ball 2. And I don't know why I'm doing this. I do not need to be having these as floats because they're already... So we have the normal because that's what this is. This is the normal vector, which gives us a direction, but not really a distance. Well, the distance is 1, but whatever. Anything times 1 is the same value. So this will give us a distance of 1 in any direction. And then if we multiply it by our overlap, then it'll give us our overlap in a specific direction for x and y. And we're doing that, and we're taking ball 1 and moving it in the opposite direction, and then ball 2 and moving it in that direction. So yeah, that's what's happening there. And then we have our next loop. So that above this loop is our static collisions. Now we're going to handle our dynamic collisions. This is a little more complicated. So we're going to loop through all the collisions that we found from the static collisions loop. And we're going to get ball 1 and ball 2. Make sure if they exist. If they don't, then don't do the rest of the logic. Get the distance between the center points of both balls. Find the normal again. This formula should look familiar. And then we're going to flip it by 90 degrees to get the tangent. So we're going to need to determine the velocity in the direction that the balls hit each other at. And we're also going to need to determine the velocity and the 90-degree angle, which is called, I think, the sliding direction of both balls. So that's why we have what we're calling the tangent here. And I believe the tangent is just a line that lies on the circumference of a circle. But in this case, it's in a 90-degree angle from the normal. And then we're taking the dot product of that tangent with our velocity for x and y for ball. We're taking the dot product for our velocity and the tangent for ball 1, and then we're doing the same thing for ball 2. And then we're taking the dot product of our velocity and the normal vector for ball 1 and doing the same thing for ball 2. And this will determine our velocity in the x and y values when we're finding the dot product between the velocity and the normal vector. And then we're going to take this dot product, which is our current velocity for x and y, and we're going to do our elastic 1D elastic or 2D 1D, I don't remember, our elastic collision formula for the velocity of ball 1 and ball 2, which is m1 and m2. And that's what this is here. And we're using dp norm as our velocity for ball 1, dp norm 1 for our velocity for ball 1, and dp norm 2 as our velocity for ball 2. Then what we're going to do down here is now we're going to take all of that stuff and actually apply it to our ball's velocity. And we're going to take the tangent, which is just the normal flip 90 degrees, and multiply it by the dot product. And all that's going to do is just move the ball in that sliding direction. There is no elastic collision happening in that direction. But when we take multiplication of the normal and the new velocity got from the elastic collision, then that's going to determine our velocity. This is our velocity in that direction. So we're just adding both of those velocities together in both directions to determine our new direction and our new velocity. And boom. And there's one thing I want to just show real quick. You'll notice I'll go back up here, and this overlap that I mentioned before, I think he had the original guy who wrote this code in C++ had 0.5 f times this, and that makes sense because you want to move the ball in both balls by that distance. But then if you move both balls halfway, then that's gonna resolve the overlap. But the problem with that is if you look at I have a printf function here. When I'm printing out the collision count, you notice, okay, in this case, the collision count is 0, but sometimes it doesn't get resolved. Did I make this afterwards? Okay, here's the case. So yeah, the collision count is still 8. That means there's still circles overlapping with each other. It isn't resolving itself. So that's why I'm not doing it this way, and I'm not multiplying it by 0.5, even though that makes sense. I guess it could be overdoing it, and if you overdo it, it could collapse still collide with a ball because you're overdoing it. But that gets a little confusing. I think if there was too many balls, that could become an issue, because if there was not enough space, then it might never be resolved at this point. But now if I do it this way and I keep running the program, I'll keep doing it for a little bit. You see that the collisions seem to always be resolved. And I say seems because there's a lot of space on the screen. If there was less space, I don't know, it might not completely be resolved. So, yeah. And that's all for the video. I hope you enjoyed. Join us now and share the software. You'll be free, hackers. You'll be free. Join us now and share the software. You'll be free, hackers. You'll be free. Hoarders can get piles of money. That is true, hackers. That is true. I can't do this anymore.